Alrighty. Lesson 3 is graph of and functions. We're going to talk about what is the graph of an equation, and then we're going to talk about an alternate way to write equations as functions. First, we need to review some basic terminology, and all of this terminology I have incorporated on that graph. Let me just make you a paragraph or give you a speech about the terminology involved in the Cartesian coordinate system. We've had a number line way back in history. We could use a number line if we just wanted to locate one point in one-dimensional space. I can show you 2 feet from that wall using a tape measure. But Rene Descartes was the dude who said, maybe we need to cross our horizontal number line with a vertical number line so that we can locate points in 2-dimensional space. 2-dimensional space is called a plane. You can imagine a plane as this wall going forever left, right, forever up, down. And if this metal strip right here is my vertical number line and this is my horizontal number line, I can name any block on this wall by telling how far from the horizontal number line it is and how far from the vertical number line it is. And these 2 vertical number lines are called what? First, let me try that again. These 2 number lines are called what?
X and Y axis.
Axis. They're called axes. Each one is an axis, plural, they are axes. The horizontal number line is called the x-axis. The vertical number line is called the y-axis, and the point where the 2 axes cross is called the origin. Awesome, awesome, awesome. The 2 number lines divide the plane up into 4 sections called quadrant, and the quadrants are numbered starting in the top right-hand quadrant. Why do you think, most things in the Western Hemisphere are read left to right? Why do you think, looking at the Cartesian coordinate system, we start here and go counterclockwise with our numbering? Any idea why this is quadrant 1? That's where your X and Y coordinates are both positive. So it seems like a reasonable place to start. Any point is named with an ordered pair. An ordered pair consists of 2 numbers in parentheses separated by a comma. And you call the first number the X coordinate, second number the Y coordinate. And like Emily, one of Emily's 2 cousins, Emily, Brittany, and Maddie. Okay. Like Maddie said, in the first quadrant, both coordinates are positive. I'll let you put that in. In the second quadrant, what's the sign of your X coordinate? You're to the left of the y-axis, so your X's are negative and your Y's are, you're above the x-axis, so your Y's are positive. What about the third quadrant? They're both negative because from the origin to get a point in the third quadrant, you go left and down. Left and down means both coordinates are negative. And then in the fourth quadrant, your X's are positive and your Y's are negative. So to locate any point in the plane, the X coordinate tells you how far to count left or right of the origin, and the Y coordinate tells you how far to graph above or how far to go up and down from the origin. Just to make sure everybody's totally okay with this so we can go on to the next thing, plot those 5 ordered pairs on this graph and label them A, B, C, D, and E. Let's make sure we all have the ordered pairs in the right place. What quadrant do you have your point A in? That's quadrant 2. You use Roman numeral, that's 2. B is in quadrant 3 because both coordinates are negative. C is in quadrant, which quadrant? 4 because your X is positive and your Y is negative. That's Roman numeral 4. What about D? Whenever X is 0, what does that tell you about the point? Which one? I heard both. Is it on the X-axis or the Y-axis? The X tells you how far to go left and right. So if X is 0, you don't go left and right. You just go up or down, in this case, up to 4. So here's point D on the Y-axis. And then what about point E? X-axis. And not only points D and E, but any point where the X is 0, you're on the Y-axis. You haven't gone left or right, you've just gone up or down. So if X is 0, you're on the Y-axis. And if Y is 0, you haven't gone up or down, you've just gone left and right, you're on the X-axis. All right. The graph of an equation is simply a picture of the ordered pairs that are solutions of the equation. And I think that some folks, I don't know when you start graphing lines, 8th grade or so, some folks don't get that what they're actually doing is drawing a picture of the solutions. When I just solve equations in lesson, whatever the previous one was, 2, like if I solve the equation x plus 1 equals 4, there's only one answer to that, and I write it as x equals 3. That's the only solution. But when I'm given an equation like y equals negative x plus 3, there are infinitely many ordered pairs that make that equation true. Now, if you know a little something about graphs, you already know the shape of this graph is what? Anybody recognize the shape of that graph? Justin, what's your pencil saying? I don't think you did know. Your pencil knew. Okay. It's not talking to you. Nobody recognizes what kind of line? Oh, oops, I said the answer. Now can somebody tell me the shape of that graph? It's a line. And the reason that I know that is it's a first degree equation. Now let's play like I don't know that. And I'm trying to figure it out. Well, if you give me some function or some equation, you ask me to graph it, and I have no idea what it looks like, what can I always do? Find some points on the line. Yeah, I can make a table. I can any, choose some x's, plug them into the equation, calculate the y value, and that will give me a set of ordered pairs that I can graph. Every ordered pair that I plot is a solution to that equation, and there are infinitely many solutions in between any two ordered pairs. That's why we end up with a solid, in this case, a solid line, and in example 2, something else. So let's see, for the equation, complete the table, plot the points, connect the points with a smooth graph. What kind of x's could I put into that equation? Is there anything that would blow up that equation, cause it to be undefined? No, you give me any number in the whole wide world, I can take the opposite of it and then add 3. So trying to think. We've used the word domain. We had the word domain in lesson 1. It was anything for which the expression is undefined, or excuse me, anything for which the function is defined. This domain is negative infinity to infinity because I can let x be anything. If I have no idea what shape this is, I better choose bunches of x's. Some positive, some negative, 0. I'm trying to get a picture of this graph. So I'm going to say let x be any, miny, miny, mo, -2, -1, 0, 1, and 2. And you could choose 5 different values for x. Everybody in here could choose 5 different x's, but we would all get the same graph, because if we calculate our y's correctly, each of these ordered pairs are solutions to that equation and lie on that graph. If x is -2, then this is the opposite of x is +2, plus 3 is 5. And that means the ordered pair -2, 5 is a solution to that equation, and -2, 5 is a point on that graph. If I let x be -1, then the opposite of -1 is +1, and +1 plus 3 is 4. That means -1, 4 is a solution to that equation, and it's a point on the graph. Let x be 0. -0 is the same as +0, and 0 plus 3 is 3. So 0, 3 is a point on the graph. If I let x be 1, then -1 plus 3 is 2, and 1, 2 is a point on the graph. Then if I let x be 2, this would become -2 plus 3, that's 1. So the point 2, 1 is on the graph. And the reason that I came up with so many ordered pairs, again, I'm pretending to have forgotten that that was going to be a straight line, and I needed to graph several points to confirm it. Let's plot these points. -2, 5 is up here. -1, 4 is right there. 0, 3. 2, 1. Oh, I don't care how beautiful your graphs are. You're going to find out that my graphs are not very beautiful. If I can see that this is an attempt at a straight line, you don't have to bring graph paper and a ruler to class with you. I'm pitifully unartistic. You can do at least that well, and that's good enough. Notice that the equation in this example is what degree? What does degree mean when I'm looking at an expression? Shelby? What's the exponent, the highest exponent of x in the equation? This is a linear equation, because that's what first degree means, and its graph is a line. So anytime I see a linear equation, I know it's going to be a line. How many points does it actually take to graph a line? Just 2. You give me any 2 points in the whole wide world and I can connect them with a line. So it only takes 2 points to graph a line. Why do we usually find at least 3? You think of a reason? Tell me.
There's not a curve.
Well, I know what shape it's supposed to be, because now I can recognize it's first degree, and first degree is always a line. So why do I need more than 2 points? Tell me, Sydney, what you were thinking. Okay, but I know the shape's a line.
See if it keeps going.
If I only choose 2 points, let's say I chose these two, -2, 5 and -1, 4, I could put a line through them, but I couldn't be certain that was right. unless I had a third point that was on the same line. So we just usually pick at least 3 points to graph a line, so that the third one can serve as a checkpoint. If I had these 2 lines, or these 2 points, and then my third point was over here, I know something's wrong. I don't know what's wrong, I have to go back and check all my work, but I know something's wrong because that should be a line. All right. Example 2, I don't know what shape it is, but I can tell you for sure it's not a line. How can you tell that number 2 is not going to be a line? Other than 1. It's a second degree equation, and later, I'll give you the word now, but later we'll talk about it more. A second degree equation is called a quadratic equation. So when I say something about a linear equation, it's a first degree equation. When I say something about a quadratic equation, it's a second degree equation. Now, we'll figure out that last blank in just a minute. What's the domain of this expression in number 2? What can I let x be? Anything. Any number in the whole wide world, I can square it and then multiply by -1 and then add 4. If it helps me, I can write that as -1 times x squared plus 4. I'm going to square it, multiply by -1, then add 4. And the domain is -infinity to infinity, because I can do that to any number in the whole wide world. So I'm going to be boring again. Use the same x's. Some positive, some negatives, 0. But all of us could choose different x's, and we would still have the same line. All right, I'm going to substitute each of those x's into the equation. I'm going to square it. -2 squared is 4. Multiply by -1. That's -4. And then add 4. That would give me 0. If you need to write down something you can see, you could write that down. -1 times -2 squared plus 4 is 0. So that means the ordered pair -2, 0 is a solution to that equation, and it's a point on the graph. I can't say it's a point on the line because I know this is not a line. And you let x be -1. Put -1 into that equation. And you'll get y equals 3. So the ordered pair -1, 3 is a solution to that equation, and it's a point on the graph. If you let x be 0, get y equals 4. So the ordered pair 0, 4 is on the graph. Let x be 1. Get y is 3. So the ordered pair 1, 3 is on the graph. And then finally, if you let x be 2, you get y is 0 again. So if x is 2, y is 0, and that's another point on the graph. pairs and connect them with a nice smooth curve. And then tell me if shape of that curve, if you recognize it as something that has a special name. What I get when I connect those 5 points. And then I can see that as x's get bigger and bigger here, my y's are going to keep getting smaller forever. And as my x's keep getting more and more negative, my y's keep getting smaller forever. Anybody happen to remember the name of that nice smooth U-shaped graph? Like, your yawn, I thought you were fixing to say it because it started with the letter your mouth was making when you started that yawn. You've had statistics, haven't you? Okay, no, it's not a bell-shaped curve, but that is kind of a U-shaped graph. I know where you got that. Miss Sydney, what do you think? It's a parabola. Does that ring a bell? A parabola is not a flesh-eating virus. It is a nice, smooth, U-shaped curve that comes from a quadratic equation. Now, the lesson that I just videotaped for you, and I'll put it on YouTube right after class. We talk about how to recognize different equations and what their graph is going to look like. You know now that any linear equation, any first degree equation is going to give you a line, and any quadratic equation, any second degree equation is going to give you a parabola. But we're going to talk about other basic graphs like the cube function, the cube root function, the absolute value function. That's what the next lesson's about. For right now, we don't know, so we make a big XY chart to figure out what a graph looks like. All right, special characteristics of graphs. One thing that we're always interested in for various reasons. You don't really know why you learn something until you do a problem, a word problem using that something. But something that's important to tell about a graph is its intercepts. Its intercepts are where the graph crosses the axes. For example, here, I would say my x-intercepts, if I had been asked for them, are the two ordered pairs where the graph crosses the x-axis. That's -2, 0, and +2, 0, where the graph crosses the x-axis. And what's the y-intercept? It's 4. You can just call it 4, or you can write it as an ordered pair. As an ordered pair, what would it be? You're on the y-axis, then the x is 0, and in this case, the y is 4. Remember up here, we said any point that is on the x-axis, the y is 0, and any point that's on the y-axis, x is 0. So we're looking for those points that are on the x or y axis. And so the next 3 problems say find the intercepts. If you give me a graph like number 3, I can just look at it and see where it crosses each axis. If you give me an equation like number 1 and 2, how can I find the x-intercept? We just said what's true of any point on the x-axis. Practice my names. James, can you tell me anything about any point that's sitting on the x-axis? The y is 0. So the x-intercept, I can let y be 0. And then James, since you answered that one so well, you made it easier for, oh, darn it, I'm losing folks. Harley, Shelby, Sydney, Lainey, I know Lainey. I was trying to think. Actually, Lainey, I was trying to think of your name. Can you tell me how to find the y-intercept? Yeah, because any point on the y-axis, the x is 0. Get to you in a minute. Just remembered your name. All right. So let's do number 3 first. This is the easy one. The x-intercepts are where it crosses the x-axis. How many times does a squirrely graph touch the x-axis? 3. Once at the point -3, 0. Once at the point -3/2, 0. And once at the point 4.5, 0. What do all 3 of those points have in common? Y is 0. How many times does this graph touch the y-axis? Also 3 times. The points 0, 3, the point 0, -4/3, and the point 0, -3.5. What do all those points have in common? The x is 0. I really should have had those 2 examples. Oh, you know what? I just realized these 2 were the 2 that we just graphed. That's why I have them before this one. Number 1 is this graph. And we can see on this graph, the x-intercept is what? Across the x-axis.
3.
And if I write that as an ordered pair, what would it be? 3, 0. And where does this graph cross the y-axis? 0, 3. This -x² + 4 is this graph on the previous page. And we already wrote its intercepts right there because I forgot. But I typed it on the second page. On number 2, we said the x-intercepts are -2, 0, and 2, 0. And the y-intercept was 0, 4. All right, those 3, we got the intercepts by looking at the graph, either the graph we were given or the graph we had done on the previous page. So it's easy to get the intercepts if you're looking at a graph. And actually, you've already helped me figure out how we find the intercepts without looking at the graph. You told me to find the y-intercept. You let x be 0. And to find the to find the x-intercept, you let y be 0. So if we looked at this equation, it's the same graph as this, but if I wanted to get the intercepts without having to graph it, to get the y-intercept, I'd let x be 0. I'd have y equals -0² + 4. where the y-intercept was 4. I write it as an ordered pair, it's 0, 4. That's what we got up here when we were looking at the graph. Yeah, same thing. To find the x-intercepts, let y be 0. 0 equals negative x squared plus 4. Now that's a little bit harder to solve. I have to solve it for x. What 3 things do I have to do to solve that for x? I would subtract the 4. Or negative 1. Divide by that negative 1. 4 equals x squared. And then what? Take the square root of both sides. And this is getting a tiny bit ahead of ourselves. Look there that you can square and get 4. There are 2. What are they? There are 2 square roots of 4, positive 2 and negative 2. Okay, plus or minus 2. So my x-intercepts are negative 2, 0 and positive 2, 0. That's what we got from looking at the graph at the top of the page? Yes. So we can find intercepts either by looking at the graph or algebraically, we can find the y-intercept by letting x be 0, find the x-intercept by letting y be 0. Now, if I wanted to put these 3 problems on the test, I'm asking you to evaluate that expression for different values of x. If I wanted to put this on the test, I'd have to type this whole sentence for number 1, evaluate y equals negative x squared plus 4, 4x equals negative 1. And then if I wanted you to do that for a different number, I'd have to retype the whole sentence. Evaluate y equals negative x squared plus 4, 4x equals 0. And then for a different number, I'd have to write the whole sentence again. Well, there's a way that I could avoid having to write that whole sentence 3 times. That's using function notation. Function notation, well, we'll get to it in just a minute, and I'm sure you've seen it before. But function notation is just a shortcut way of writing all 3 of those sentences without having to write so much. So let's talk about what a function is. Before we can talk about what a function is, we have some other terminology that we have to cover. A relation. A relation is just any set of ordered pairs in the whole wide world. They may make sense, like how tall you are, comma, your shoe size. Usually taller people have bigger feet, not always. Or people usually have shorter feet. That would make sense as a set of ordered pairs. But the ordered pairs don't always have to make sense. It could be the first letter on your license plate, comma, the name of your pet. I know the relationship between your license plate and your pet. Like your pet is a male dog, isn't it? Relationship. Male dogs pee on everything. You can't license plate. But anything that can be described as a set of ordered pairs is a relation. Anything in the whole wide world. The domain of the relation, we've used the word before, it's the set of all x values or input values for which the function is defined. It's any number we can put into the function that won't blow it up. The range of a relation is the set of all y values that can be obtained by the function. You put in x's, y's come out. If x is any element in the domain, x is called your independent variable. You give me any number in the whole wide world that's in the domain And it's my independent variable, it's independent of anything else. But once I've chosen my x, the y that I get depends on the x that I put in. So y is called your dependent variable. It depends on the x that you put in. And with all of those terms defined now, we can talk about what a function is. A function is a specific kind of relation. Specifically, a function is a relation for which each element in the domain, we said the elements in the domain are called your x's. For each x in the domain, there's exactly one element in the range. That's your y. Meaning for each x, there's only one y. I like to think of it as for each question, there's only one answer. If I say, I'm gonna a name, and that person's gonna tell me their shoe size, that would be a function because each of you only has one shoe size. Could possibly have. But assume that's not the case, then it's a function because each person only has one shoe size. Now, what if I said, I'm gonna call out a shoe size, everybody who wears that shoe size, raise your hand. If I called out an 8.5, would that be a function? I said, who wears an 8.5? Would there be more than one person who wears that size? Yeah, so that's not a function. A function for each question, there's only one answer. Many of the buttons on your calculator are functions. The x squared button, it's a function. Every single time I ask it, what is -3 squared? It says 9. Every time, there's only one answer to that question. It is a function. X cubed is a function. If I say cube this number for me, the calculator is only going to give me one answer. So that is a function. I like to think of a function as a machine. It's a machine that has a job. For example, if I built a function that I put in a 3 and it spit out a 7, I'd go, this must be an adding 4 machine. That's a logical assumption. I guess there are other things you can do to 3 to get 7, but the most obvious one is adding 4. If the next time I put in a 3, I got out an 8, all of a sudden my machine has gone crazy. I put in the same X and it gave me 2 different Y's. I don't know what that machine's doing. It's not functioning. It's not a function. That makes sense? All right. For each X, there can only be one Y. There are many different ways we can describe a relation. We can use words like first letter of your license plate, comma, pet's name. That would be a word correspondence. We could use sets of ordered pairs, or we could use an equation. So we're going to look at examples of each of those. And for each one, I want you to tell me if the relation is a function and why. These first 2 are word correspondences. And the first one, I give you the domain is the set of all of your names. Let's say all of your names are in a hat. I'm going to pull out one. And then I'm going to ask that person, what's your age? The range is going to be the set of non-negative integers. Nobody is a negative age. Technically, you could be 19.5, but usually we give our age as a whole number. So if the domain is all your names, the relation, I'm going to put a name in the machine's going to spit out an age. Would that be a function? No matter whose name I pull out of the hat, how old, how many different ages could that person be? just one. So that is a function because each person only has one age. If I define the relation in a different way, it might not be a function. If I say, now it's numbers in the hat. I'm gonna pull out a number and I'm gonna say, tell me your name if you're this age. Would that be a function? Because for any age I pull out, there's likely to be more than one person who is that age. So no, that's not a function because each age could correspond to multiple people. If my X is an age and my Y is a name, there could be one X that had more than one Y. Not a function. Y'all know me well enough to know it would be okay to throw your hand up in the air or shout if you had a question. Okay. The next three examples, I'm defining a relation to be a set of ordered pairs. So in number 3, how do you find the domain of this relation? What did we say domain meant? The x's for which the function is defined. Well, we only have 3 ordered pairs, and what x's do they have? 7 and 3. That's the domain of that relation. What's the range of that relation? And you don't have to write the 4 twice. If I say, what are the y values obtained by this function? You would just say 2 and 4 are the only y values this function gives me. Now, for mapping, I just mean draw a line from each x to the y that it corresponds to. In the first ordered pair, draw a line from the 5 to the 2. In the second ordered pair, 7 corresponds to 4. And in the third ordered pair, 3 corresponds to 4. Does that look like a function or not a function to you? Question mark after it, right? No, I don't think so, but I wouldn't stake my life on it. Think of the definition of a function. For each x, there's only one y. What if I said, how many different y values are there when x equals 7? And that's the only thing x is, or excuse me, y is when x is 7. That's like, I could call 2 different names and they happen to be the same age, but that was still a function because each one of you only has one age. Each x here only has one line going from it to something else. So for each x, there's only one y. Is that a function? Let me write this one down and then we'll compare it to number 4 and I think you'll see the difference. This is a function because each x, I'm going to say, is only mapped to one y. Is the 7 only going to one y value? Yes. Is the 3 only going to one y value? Yes. Does it matter that they go to the same y value? That's not part of the definition of function. It doesn't matter if two x's have the same y. It only matters if one x has two different y's. I think that's what happens in the next example. I have three ordered pairs. The domain, if I say what for what x values is this relation defined? The only x's are 1 and 2. And what are the y's? 2, 3, and 5. Now go back and fill in the mapping. In the first ordered pair, 1 corresponds to 2. In the second ordered pair, 1 corresponds to 3. And in the third ordered pair, 2 corresponds to 5. Is that a function? No. Because 1x corresponds, or I could have said is mapped to more than 1 y. These two mappings and see if you can tell what makes this one a function, but this one is not a function. 7 only goes to one number, 3 only goes to one number. It doesn't matter, they go to the same number. The only stipulation in the definition of function is each x only goes to one y, which is the case here, but is not the case here. If I built a button on my calculator to represent these ordered pairs, one time I entered 1 and hit that button, it would spit out a 2. The next time I entered 1 and hit that button, it would spit out a 3. That would drive me nuts. That's one question that has two different answers, and that's not a function. Now, is that okay? I could tell if, if you're getting kind of fuzzy there, like. Okay. Another way to describe relations is with equations. The next 3 examples, we have equations. And number 5, I want you to be able to read that notation because we're going to see it again. I didn't use that notation in number 6 and 7. I just wrote the equation. But in number 5, you read this notation. The braces indicate a set. This is a set of ordered pairs of the form x comma y. This vertical line is in set notation. It's my such that. All the ordered pairs such that the y is the x plus 1. For all the ordered pairs where the y is 1 bigger than the x. Somebody give me an ordered pair where the y is 1 bigger than the x. 0, 1. Okay, 0, 1 is certainly one ordered pair where the y is 1 bigger than the x. Give me another one. That certainly works. Can somebody give me one with a negative x? And then 1 bigger than that is negative 1. So we found 3 ordered pairs that were solutions to that equation or made that equation true. What's the domain of that equation or that relation? I was a little bit sneaky. Why did I pay you to say that? So I could explain why it's wrong. In 3 and 4, these were the only ordered pairs for which the function or the relation was defined. I was given all the ordered pairs, so the domain was just the x's and the range was just the y's. But here I'm saying any ordered pair where the y is one more than the x is the relation. So how many ordered pairs make that equation true? Only these three that make it true? There are infinitely many that make that true. Domain is the set of x's which can be used in this function. What x's can have one added to it? Any x in the whole wide world. That domain is not just the three sample ordered pairs we found, but any ordered pairs that satisfy that equation. And you could let x be infinitely big, infinitely small, positive, negative, zero, anything. You see the difference between me giving you just three ordered pairs and me giving you an equation and knowing there's infinitely many ordered pairs. I just found three of them. What about the range? What kind of y values could come shooting out of adding one machine? Anything. I could put in any x, add one to it. I could get big y's, I could get negative or little y's, negative y's. I could get anything out of that machine. So the range is -1 to infinity, or negative infinity to infinity also. If I put an adding one button on my calculator, each time I put in an x, how many right answers would there be to what's one more than the number I just put in? How many right answers would there be? Just one. If I put in a 7, it spits out an 8 every time. If I put in a -2, it spits out a -1 every time. So is that a relation? Is that a function? Yes. Because for each x, there is only one x plus 1. And that's what y is in this relation. Right? Number 6, what about the relation y equals x squared? Give me some ordered pairs where the y is the square of the x. I just remembered your name. Give me one. The y is the square of the x. Yes, please give me an ordered pair where the y is the square of the x. One what? Oh, if you put in a 1 and you squared it. Oh, okay, I'm sorry. Y'all gotta holler at me. I'm getting deaf at my old age. 2, 4. Because the y is the square of that x. Good job, Chloe. Isaac, can you give me another one where the y is the square of the x? That'll work. 4/16. Could somebody give me such an ordered pair, but where the x is negative? Maybe give me one where the x is negative. -2, 4 would also work. Again, because the y is the same as the x. What about the domain of that relation? What kind of x's can I square? I can square anything in the whole wide world if you give me a calculator. The domain's -infinity to infinity. What kind of y values can you get from squaring x's? Only positive numbers? Can I get a negative number from squaring an x? Can't get a negative number. There's one number I can get that's not positive though. 0. So what's the range? 0 to infinity, not just the positives, but 0 to infinity would be the y values that can be obtained from that relation. Is that relation a function? For each x, is there only one y? Does it matter that two different x's had the same y? It didn't matter up here when two different x's had the same y. The problem is when one x has two different y's. So this is a function because for each x, there is only one x squared. Right? What about number 7? Can you give me some ordered pairs where the x is the square of the y? Two. Oops, I don't know why I wrote -2 when you said 2. Yeah. Or 2. Somebody give me another ordered pair where the x is the square of the y. 9, 3 definitely work. And somebody give me one with a negative y value. -2. Can somebody give me one with a negative x value? -9, -3. Would that x be the square of that y? Would the 9 be the square? I have to write it down to see it. You said, say your ordered pair again. Okay, well, I have to look at it. I can't picture anything in my head. Is that x the square of that y? What do I get when I square that y? I get a +9, and that's why that is not a solution to this. So again,
But you can't have an x. Okay.
yeah, that's my point. That's my point. When I said, can anybody give me such an ordered pair with a negative x? Several people went, no, nobody can do that. Because the domain, what x can be, doesn't include negatives. It's 0 to infinity are the only x's you can get from squaring y's. Domain's always your x's, range is always your y's. What kind of y's can you square? You can square anything in the whole wide world. So the range is -infinity to infinity. Is that relation a function?
So when you write that down like that, is it always negative infinity first?
Oh, I'm glad you asked that. I don't think I made that clear. Interval notation is always smallest to largest. So you write 0 to infinity, not infinity to 0. And for the same reason, you write negative infinity before positive infinity. It's always left to right on a number line. Is that relation a function? No? Why not? Let me write it this way. Every x except for 0 has 2 y's. When x is 4, y could either be +2 or -2. When x is 9, y could be +3 or -3. If you have one x that has different y's, not a function. All right. Just speed up a little. Got about 12 more minutes. What about when you're looking at a graph? When you're looking at a graph, domain is still your x's. But when you're looking for x's on your graph, you're really looking at how far does this graph go left to right, because that's what your x values tell you. How far does that graph go to the left? Forever. And how far does it go to the right? Forever. Its domain, this function is defined from -infinity to infinity. X values left to right, that's your domain. Your range is your y values low to high. Notation is always smallest to largest. So what's the lowest y value on that graph? 0. And what's the highest y value on that graph? Those arrows indicate that this graph goes forever up. Is the 0 included? Does this graph actually touch where y is 0? Yes, it does. Infinity can never be. It's not a number that you can get to and include. Is that relation a function? For this x right here, how many corresponding y values are there on the graph? Just one, right there. For this x, there's only one y. For this x, there's only one y. Is it true that for that graph, each x only has one corresponding height on the graph? Yeah. X value has one corresponding height, and that's what a y is, it's a height on the graph. All right, one more. What's the domain of the relation defined by that graph? The x values left to right. Somebody said it. At most x is 0, and then the x's go forever to the right, so 0 to infinity. What y values can be obtained from this graph? How low does it go to how high does it go? It goes from forever down to forever up. Is that relation a function? For this x right here, whatever it is, how many heights are there on the graph? There's one point above it, but there's one point below it. So for this x, there's two different y's. For this x, there's two different y's. For any x except for 0, there's two different y's. Is it a function? No. And I'm going to skip the because we've got to keep going. What that just illustrated is something you may remember from algebra. What is that thing that says if at any point on a graph, a vertical line can be drawn such that it touches the graph in more than one point, then the graph is not the graph of a function. Remember the name of that? That's your vertical line test. And we can see that the graph in number 8 would pass the vertical line test. No matter where I put a vertical line, it would only touch the graph in one place. But number 9, the graph would fail the vertical line test. There are multiple vertical lines that would touch the graph in more than one place, and therefore it's not the graph of a function. All right, so going back to this idea of, man, I wish I didn't have to write that whole sentence 3 times to get you to do these 3 problems on the test. I said I wouldn't have to write all that if I used function notation. Well, here's function notation. We usually call our generic functions f of x. In business calculus, we have a revenue function, we call it r of x. We have a profit function, we call it p of x. But if I'm not doing a word problem where I know what the thing stands for, I just use f of x. F is the name of the function. X is the name of the independent variable. It's the input value, what you put into this function. 3x plus 2 is called the defining expression. It tells you what this function does. What's the function of this function? And f of x together is the y value. Add y right there. It's the y value of the function at a given x. So f is the name of the function, x is what you put in, 3x plus 2 is what the function does, and then it spits out a y. The y is the same as f of x. So I've given you 3 functions right here, and I've asked you to find function values. G of 2 means use the function g and do what with it? How do I find g of 2? In place of all the x's. -2 times 2 squared plus 2 minus 1. I just put 2 in place of both of those x's. Let me go ahead and just real quickly say that would be -8 plus 2 is -6 minus 1 is -7. I want to double check that. -8 plus 2 minus 1. Yeah, it'd be -7. Number 2 says find h of 2. That means put 2 in place of all the x's in the function h. Well, function h is a weird little function. Sometimes we call it the constant function, because no matter what you put in, h always spits out 7s. If you put in a 2, h will spit out a 7. If you put in a 3, h will spit out a 7. Anytime you have a function that's always gives you the same number, that's called a constant function. F of -x, what do you think that means? If f of 2 means put 2 in the place of x, f of -x would mean put -x in the place of x. In the function f, this function, I'm just going to put a -x wherever there was an x, and then I'm going to clean it up as much as possible. Not much I can do there other than to say 2 times -x is -2x. Right? It doesn't say put -x in the place of x. it says take f of x and multiply it by what? -1. That's -1 times f of x. So -1 times whatever f of x is. F of x is 2x plus 1. When I multiply that by -1, I get -2x minus 1. Notice these aren't the same thing. F of -x is not the same as negative f of x. All right, I'm gonna have time to do one difference quotient, and then we're gonna be out of time, and I so wish I had 15 more minutes. Because I need to finish the video, like I did last time. When I run out of time, I hang around and do the end of the video and then put it on YouTube. If you need to watch, I'd say the last 15 minutes of the notes. It'll be on YouTube in a few minutes. But let's do one of these difference quotients. That's something that is important in calculus. And most of you probably aren't going to calculus, but if you do, you'll see this expression there. I think of it as a recipe with 3 steps. The first step is find x plus h. Just put x plus h into the function. The second step is subtract the function. And the third step is divide by h. So I'm going to do these 3 steps every time I'm given the difference quotient.